All right, so now we're going to look at geometric series, and so this would be an infinite sum, so that we're adding up an infinite number of terms. The question we need to ask ourselves here is, when would this have a sum? As we're adding up an infinite number of terms, it's possible that the sum would just tend to infinity. In other words, get larger and larger and larger. But that's not always what happens. It actually depends on the value of r. So if we look at the formula for the nth partial sum, when, of course, r can't be equal to 1, right? If r is equal to 1, then we just have all the terms are the same. That wouldn't be interesting. That's not geometric. And of course, in the formula, you can see you can't divide by 0. So let's consider the value of s sub n. Oops. As we let the number of terms tend to infinity, right? We want to let this become an infinite sum. Oh, excuse me. So this r sub n here, if n is getting big, right, this is the number where things happen if n is getting large. The rest are constants, depending, of course, they can change depending on what a sub 1 and r are, but for a certain series, those would be constant. The n is what's changing. So if r is bigger than 1, that's going to become infinite. So r sub n will, whoops, I don't know why I wrote a 2. Let me start over. Will tend to infinity if r is bigger than 1 or less than -1, which we could say, use absolute value, is bigger than 1, because r can be positive or negative. Excuse me. What was I going to say? Okay, so what will happen if r is a small number, like 1/2, when I say small, I mean between 0 and 1, like 1/2, 1/3, or 0.6, or anything like that, is when you raise it to the nth power, that will actually tend to 0. And so I was using r positive, but that would be if r is positive or negative and close to 0. So if absolute value of r is less than 1, or in other words, -1 is less than r is less than 1. So if r is between -1 and 1, then this will tend to 0. So let's see. Looks like here when r was 0.7, here's the first term, and then you take it times 0.7 times 0.7. The numbers are getting smaller. That's what I'm saying. They're going to tend to 0. If r is bigger than 1, that number is going to get bigger and bigger and bigger. Excuse me. So what does that mean? Well, what that means is this will not approach a constant number, or a limit, we call it, if r is bigger than 1 or less than -1. But it will approach a constant if r is between -1 and 1. And if this is going to 0, then this term becomes, or this factor becomes 1, and our sum approaches a sub 1 over 1 minus r. If n is going to infinity and the absolute value of r is less than 1. Okay, so that's the only time the geometric series has a sum, is when r is between -1 and 1. And that's what this theorem is saying right here. So if r is bigger than or equal to 1, then the series does not have a sum. And we're not really interested in r being equal to 1. Okay, so here we have a series 1/2 plus 1/4 plus 1/8. That's a geometric series because if you take 1/2 times 1/2, you get a 1/4. If you take that times a 1/2, you get an 1/8. If you take that times a 1/2, you get a 1/16, and so forth. So find the sum using the formula for the sum of an infinite geometric series. All we need for this is actually an easier formula than the nth partial sum. Oops, I'm sorry, I'm off the screen here. A sub 1 is a 1/2, r is a 1/2, so s, we just call it s instead of s sub n, is 1/2 over 1 minus 1/2, or 1/2 divided by 1/2, which is 1. So a real simple formula to use. And this one is actually really easy to verify using a geometric argument. If you take a whole of something, I'm going to use a box, so this is, or a square I should say, and this is your whole, this is 1. Cut it in half, right? And then cut the half in half. Now you got a 1/4, so you're adding a 1/2 plus a 1/4. Now just keep cutting what's left in half. That's an 1/8, a 1/16, and so forth. And you can see that you could do this forever and ever and ever. And as you're adding up, you just get closer and closer to the whole, which is 1. All right, the next problem, again, we have a geometric series. A sub 1 is 2. R is 1/5, I'm sorry. Notice how the numerator stays constant. It's just the denominator, we're getting multiples of 5. So r is 1/5, therefore s is 2 over 1 minus 1/5, 2 over 4/5, or 2 times 5/4, which is 5/2. That's it. Pretty simple formula. All right, here's another place we could use this idea. We know that a non-terminating but repeating decimal is a rational number. And a rational number can be expressed as a ratio of 2 integers. So this is a rational number, and it can be expressed as a ratio of 2 integers. But it can also be expressed as a geometric series. So when we take 2.35151, etc., that is equal to, so we take the part that doesn't repeat, and then look at the part that repeats, and add to this, so we need a decimal of 0 where the 3 is here, so 0.051, so you want to add, and that would give you that much, right? And then the next number will be 0.000, so you want all 3 places here, and then 51. So when you add that, you'd get the next repeat, right, of 51, and etc. So now we'll have 5 zeros, 5, 1, and this goes on forever. So this part is easy to express as a fraction. It's 2 3/10 or 23/10. So now the rest of these are easy to also express as a fraction because they don't repeat. This is 51 over 1,000. This is 51 over, so 1, 2, 5 zeros. And this would be 51 over 1, 2, 3, 4, 5, 6, 7, right? The number of places should match the number of zeros. 2, 3, 4, 5, 6, 7, etc. So this is geometric because notice the 51 over 1,000, if we multiply that times 1 over 100, 2 more zeros, we'd get the next term. And then if we multiply that times 1 over 100 again, then we get the 2 more zeros, we get the next term. So 51 over 1,000 plus 51 over 1,000 times 1 over 100, and then 1 over 100 squared, etc. So this is geometric. At least this part is, right? Since that's geometric, and in this case, a sub 1 is 51 over 1,000, and r is equal to 1 over 100. Since r is less than 1, we can use the formula for an infinite geometric series. So this is 23 over 10 plus a sub 1 is 51 over 1,000 over 1 minus 1 over 100. So 23 tenths plus 51 over 1,000 over, so this would be 100 over 100, 99 over 100. So 23 tenths plus, let's see, let's do this, 51 over 1,000 times 100 over 99. So we're just left with a 10 there. So we get 23 over 10 plus 51 over 990, which means now we need a common denominator, which will be 990. So I'll take 23 times 99, whoops, which is 2,277. So we end up with 2,328 over 990. And that, it does simplify. They're obviously both even. But if you got that far, I'd be happy. Let's see, divided by 2. 990 divided by 2. So this would become 1164 over 495. 2, 8, 12. It looks like 3 might go into both of those if I added right. No, 3 doesn't go. What was I thinking? 3 doesn't go in. Oh, yes, it does. 13 and 5 is 18. Yeah, 495 divided by 3. I shouldn't have wrote so big. 388 over 165. 7 and 5. 12. Okay, 3 doesn't go into the numerator. Okay, I think that's it. So now let's double check. So when I divide this, if I did this simplifying, right? Yep, so we get that decimal number that we started with. So that would be simplified. Again, even if you just got this far, I'd be pretty happy. So it just, because it just says find a fraction. It doesn't have to be the simplest one, right? But all of these would work. Okay, so there's another place where we could use that formula.